Hello friends, so today we are going to solve questions from modern physics, and from the year 2000 there are total 5 questions, and from the year 2001 there are also 5 questions. So in total we are going to solve these 10 questions. So in the first question, it was asked in the year 2000, and it states that imagine an atom made of proton and hypothetical particle of double the mass of electron but having the same charge as of electron. Apply the Bohr atom model and consider all possible transition of this hypothetical particle to the first excited level. The longest wavelength photon that will be emitted has a wavelength lambda given in terms of Rydberg constant R for the hydrogen atom equal to. So we are here going to find out the, you can say, the wavelength in terms of the Rydberg constant, that is our value of R. And we are given that we are having an atom. It is made of a proton and hypothetical particle which is having a double the mass of electron but charge is same, that of electron. So it means our atom will be consisting of two particles. One is of a proton and second one is a particle which is having a negative charge that is equivalent to the electron. And the relationship between the mass is given, that we have said that the mass of the particle let us suppose that is of m is equal to twice the mass of electron. Mass of electron. Let us suppose we call this as me. So from here we can write that the mass of particle will be equal to twice the mass of electron. And it says that to the first excited level, so first excited level means value of n will be equal to 2. First excited level, which means value of n is equal to 2. And next we are going to write the equation for the energy level in the Bohr model. That is our standard equation. You can say energy levels in Bohr model, and for nth energy level, if energy is given as E of n, then we can write that our E of n is equal to, this is our minus m e raised to power 4 and here we have a epsilon naught square h square and multiply by 1 upon n square. And in terms of hypothetical particle, if we substitute all the values, we can write this will be equal to minus 13.6 multiplied by z square. Mass of hypothetical particle is, we have taken as m, or for the sake of let us call this as m prime, much more easier to differentiate. So this comes as multiplied by m prime and divided by our mass of electron and into 1 upon n square, and this energy is in electron volt. And for a hydrogen like atom, we can say that the value of z will be equal to 1, and we are given that the mass of our particle, that is m prime, is our mass of particle. This is equal to twice the mass of the electron. So from here we can just drive an important conclusion that energy becomes double compared to hydrogen atom. Double compared to hydrogen. And therefore, based on this, we can find out the modified Rydberg constant. So we can say modified Rydberg constant let us call this as r prime, which will be equal to mass of the particle m prime divided by mass of electron and multiply by original constant, that is our r, and its ratio is our 2. So therefore we can write that our r prime is equal to 2 times r. So this gives us relationship between our new Rydberg constant as compared to the original one. Now we are going to find out the longest wavelength. So we can say longest wavelength photon which is basically lowest energy transition to the level n is equal to 2. And we have to find out the longest wavelength, and for the longest wavelength the photon should be, you can say, emitted to n is equal to 2. We are going to consider the smallest energy transition, okay, because longest wavelength is going to give us a smallest energy transition. So we can say, considering smallest energy transition. Smallest energy transition into n is equal to 2. So we can say that from n is equal to 3 to n is equal to 2. So based on this, we are going to solve our energy difference. Energy difference, that is our delta E, will be equal to energy at level 3 minus energy at level 2. And we can generalize the formula in terms of Rydberg constant, but the modified Rydberg constant, that is R prime, 1 upon 2 square minus 1 upon 3 square. We substitute this as our 2R, giving us 1 upon 4 minus 1 upon 9, and this gives us 5R upon 18. And we already know the relationship between the energy difference and the wavelength. So we can say our wavelength lambda will be equal to hc upon the change in energy. This comes as our so we can write this as our lambda is equal to 1 upon delta E, and this is under the condition if we consider the units of HC in terms of units of HC. So simply substitute value of delta E, we get lambda is equal to, this is our 5R and 18. Okay. So we get this is our wavelength, it's a lambda. So option number C is correct. Correct. Next question. It was also asked in the year 2000, and it states that two radioactive materials X1 and X2 have a decay constant 10 lambda and lambda respectively. If initially they have the same number of nuclei, then the ratio of number of nuclei of X1 to that of X2 will be 1 upon E after the time. So here we are given two radioactive material. One is of X1, which is having a decay constant, suppose lambda 1, that is equal to 10 times lambda, and we have another that is of X2, decay constant is suppose our lambda 2, and that is our lambda. And initially it is mentioned that they are having same number of nuclei. So you can say initially for first one, that is N1 0, is equal to the second one, that is N2 0. And it says that we have to find out time. Let us suppose this time is t. So after time t, the ratio becomes 1 upon E. So you can say after time t, ratio, which basically is our N1T upon N2T is equal to 1 upon E. Okay. So we have to find out the value of T. So it is directly based on the decay law, or we can say exponential decay law. Exponential decay law which tells us that for any time t, it's will be equal to initial value n naught e raised to power minus lambda t. So we have two samples, x1 and x2. So we can divide the equation as, for the first sample, as n1t is equal to n naught, and we can just assume that they have a equal to n naught because they are same. N naught e raised to power minus 1 lambda t, and for the second one we can write this as n2 t is equal to our n naught e raised to power minus lambda 2 t. We substitute value of lambda 1 and lambda 2, and along we take the ratio. So we get this as n1t ratio into t. N naught are going to cancel out, so we are going to get this e raised to power minus 10 lambda t, and this comes as e raised to power minus lambda t. This comes as e raised to power minus 9 lambda t, and their ratio is said to be equal to 1 upon e. Or which we can write e raised to power minus 1. So from here we can write that minus lambda 9 lambda t is equal to minus 1, giving us that the value of t is equal to 1 upon 9 times lambda. So this comes as option D is correct. Option D is correct. Next question. We are given that electrons with energy 80 kilo electron volt are incident on a tungsten target of an X-ray tube. K shell electrons of tungsten have 72.5 kilo electron volt energy. X-rays emitted by the tube contains only. So here we are given that energy of the electron is given. So we can say electron energy this is our 80 kilo electron volt, and we are also given that the K shell electrons have energy of 72.5 kilo electron volt. So we can say binding energy of K shell let us call this as W, will be equal to 72.5 electron volt. And as soon as electrons strike the target, which is made of tungsten, the X-rays are emitted. And here it is talking about the continuous X-ray, and it is also mentioned here brimstone lung is an entire spectrum, okay, which basically means that high-speed electrons, when are decelerated by the target, so that results in a range of X-ray wavelengths. So we can say that continuous spectrum is produced when high speed electrons are decelerated by the target. By target. And because of this, there is a continuous range of X-ray wavelengths. So this results in continuous range in a range of X-ray wavelengths. And in this case, we can say that our wavelength will be minimum corresponding to the maximum energy photon. You can say minimum wavelength let us suppose we write this as L minimum, lambda minimum corresponds to maximum energy photon. And we already know the relationship between our energy and wavelength. So we can write this as energy is equal to our Hc upon lambda minimum. This gives us that our lambda minimum will be equal to Hc upon E. And in terms of electron volt, our Hc is our 1240 and energy is our 80 kilo electron volt. So this comes as 80,000 electron volt, and we get our lambda minimum will be equal to 0.155 angstrom. So continuous spectrum is there, but having a minimum wavelength of 0.55 angstrom. Okay, so there are two options, option A and option B, which mentions that there is a minimum wavelength of 0.55 angstrom, 0.15 angstrom, but only difference is that the characteristics of X-ray spectrum in the tungsten. So we are going to verify that. And so basically we are going to discuss, or you can say analyze, the characteristics of X-ray. X-rays, and these are, you can say, emitted only if the incident electron energy exceeds the binding energy, which here in this case is given as 72.5 kilo electron volt. So you can say that emitted only if incident electron energy exceeds binding energy of our, in this particular case, is K shell. and that binding energy is given to us as a 72.5 kilo electron volt. And our electron energy it is given as 80 kilo electron volt. So we can just draw a conclusion that our electron energy is greater than our binding energy, that is our 72.5 kilo electron volt. So which means that characteristic X-rays are emitted when electron drop into K shell. K shell. So therefore option D is correct. D is correct. Next question. It states that a hydrogen-like atom of atomic number Z is in an excited state of quantum number 2n. It can emit a maximum energy photon of 204 electron volt. If it makes a transition to a quantum state n, a photon energy of 40.8 electron volt is emitted. Find n, z, and the ground state energy in electron volt of this atom. Also calculate the minimum energy in electron volt that can be emitted by this atom during de-excitation. Ground state energy of the hydrogen atom is minus 13.6 electron volt. So in this case, we are given that there is a hydrogen-like atom, and so basically we can say that it is having one electron and atomic number is given to us as a Z. So we are given hydrogen-like atom. So basically means there is a one electron and atomic number is Z. And in excited state, quantum number is 2n. Excited state, quantum number with quantum number is our 2n. And it is also given that the maximum energy of the photon is 204 electron volt. Okay. So we are given that maximum energy photon is our 204 electron volt. So from here we can say that transition from its quantum number, that is 2n, to 1. And it also states that if it makes a transition to quantum number state n, the emitted is 40.8. and it states that photon energy, energy of photon is our 40.8 electron volt, and this is when the transition is from 2n to n, and we are supposed to find out the quantum number, that is value of n, atomic number, as well as the energy and minimum energy also. So we start with the formula for the energy level, and we can say the energy level for nth energy level, we can write our E of n is equal to minus 13.6 Z square upon n square, and this is in electron volt. And if the transition is from Ni to Nf, transition from Ni to Nf, then difference in energy, let us call that as delta E, which will be equal to energy at our Nf minus energy at our Ni. So we substitute, we get this as 13.6 Z square, and we have this as Nf square minus 1 upon Ni square, and we are given for maximum energy the transition is from 2n to 1 and the energy is 204. So we can use the formula that for maximum photon energy rather, for maximum photon energy, value of delta E, that is our 204 electron volt, and the transition is from 2n to 1. Therefore, we can write that 204 will be equal to, and this will be over 13.6 Z square, and we have 1 minus 1 upon 4n square. This comes as 13.6 Z square 4n square minus 1 divided by 4n square, and let me rewrite the equation and call this equation number 1. 204 is equal to 13.6 Z square 4n square minus 1, and this is 4n square. Let us call this equation number 1. And secondly, when the photon energy is our 40.8, the transition is from 2n to n. So you can say for photon energy, that is our delta E is equal to 40.8, and the transition is from 2n to n. So therefore we can write that 40.8 is equal to 13.6 Z square 1 upon n square minus 1 upon 2n square and whole. And this can be sorted out and we get this as 13.6 z square. LCM will be over 4n square, and this comes as 4 minus 1, that is our 3. And we can just write it. 40.8 is equal to 13.6 z square 3 divided by 4n square. Let us call this equation number 2. So we have two equations and two unknown. So we can just solve it. And we can say from equation 1 and 2, from equation 1 and 2, we can easily find out value of z as well as n. So we are going to get value of z is equal to 2n and value of n will be equal to 2. And we can write that this value of z will be equal to, based on value of n is 2, so we get this value of z is equal to 4. And from here we can find out the ground state energy. Ground state energy, we can call this as E1, will be equal to, value of n is 1, so this comes as minus 13.6 z square, and let me write this as 1 square, doesn't matter. Value of z is our 4, so this comes as minus 13.6 into 4, 4 square. So we get our E1 will be equal to minus 217.6 electron volt. And finally, the minimum energy photon is going to emit. Minimum energy photon emitted and initial state is our 4, because that is z is equal to 2n, or we can say z is equal to 4, and which basically means that minimum energy will be emitted when there is smallest allowed transition. Smallest allowed transition. So we have 2n. So 2n is nothing but about 4. So if it comes down to 3, so that will be our smallest energy or minimum energy transformation. And therefore we can write that the energy minimum energy, that is our delta E, will be equal to 13.6 z square, and this is our 3 square minus 4 square. Z is our 4, so we get this as 13.6 into 16, and we have 1 upon 9 minus 1 upon 16. So we get that this energy delta E will be approximately equal to 10.57 electron volt. Yes. Next question. It states that when a beam of 10.6 electron volt photon intensity 2 watt per meter square falls on a platinum surface of area 1 into 10⁻⁴ meter square, work function 5.6 electron volt. 0.53% of the incident photon eject photoelectrons. Find the number of photoelectrons emitted per second and their minimum and maximum energies in electron volt. Take 1 electron volt is 1.6 into 10 to the minus 19 joules. And in this case, we are given energy of the photon. So let's write this as E photon, and this is our 10.6 electron volt. Work function is given, so our phi is also given to us as 5.6 electron volt, and we have intensity of light, photon intensity. Let us suppose that is our I. It is given as 2 watt per meter square. We are also given as area. Area is 1 into 10 to the power minus 4 meter square. And finally, it states that only 0.53% of emits the photoelectron. Basically, we can say it is efficiency, much more easy to remember. So this is 0.53%. So with respect to area as well as intensity, we can find out the total power on the surface. So you can say total power on the surface if that is given as P, then after P will be equal to intensity multiplied by area, which gives us 2 multiplied by area is 1 into 10 to the power minus 4. This gives us 2 into 10 to the power minus 4 watts. And we are given total energy in terms of electron volt. We can convert into joules. So we can energy per photon in joules. Energy per photon in joules. Energy is given to us, so we can directly write E photon, and its value is 10.6 into 1.6 into 10 to the power minus 19. This gives us 1.696 into 10 to the power minus 18 joules. Now we can find out number of photons per falling per second. Number of photons falling per second. That is our power divided by energy of the photon. And this gives us power is our 2 into 10 to the power minus 4. Energy of photon is 1.696 into 10 to the power minus 18. And this comes approximately equal to 1.179 into 10 to the power 14. And we are given that the efficiency is only 0.53%, but actual number of photons that are falling is per second is 1.179 into 10 to the power 14. So we simply multiply by the efficiency. So we can say number of photons emitted per second. Number of photons emitted per second. And let us call this as NE. and let us call this as NP. So we can say our NE will be equal to 0.53% multiplied by our NP, which is our 0.0053 into 1.179 into 10 to the power 14, and this gives us approximately 6.25 into 10 to the power 11 electron per second. Next is our maximum and minimum energies. So our maximum kinetic energy let us call this as K max will be equal to energy of photon is 10.6, that is our energy of photon minus work function, which is 10.6 minus 5.6. This gives us 5 electron volt. And here you can say we have to find out other thing, minimum energy. So the minimum energy is, if there is no, you can say, energy loss, then the minimum energy will be equal to the maximum kinetic energy. So you can say for no energy loss, minimum will be equal to our maximum, which came out as 5 electron volt. Next question. It was asked in the year 2001 and states that transition from the state n is equal to 4 to n equal to 3 in a hydrogen-like atom results in ultraviolet radiation. Infrared radiation will be obtained in the transition. So we are going to find out when the transition takes place, the resulting radiation should be our infrared. And we can say that this is related with our energy difference. So we can say energy difference that is our delta E. We are going to discuss only the, you can say, states values. The rest of the values will be constant. So this becomes 1 upon n1 square minus 1 upon n2 square, and here this is of n2 is greater than our n1. And we have to remember that both ultraviolet and infrared are at the opposite end of the spectrum, because ultraviolet is having a shortest wavelength and infrared in comparison is going to have a longer wavelength. Same analysis we can draw based on their energy. So we can say if we are having higher energy difference, this will be resulting in shorter wavelength, or in terms of the given question, we can say it is somewhat related with our ultraviolet. And if we are having low energy difference, which basically means longer wavelength, and that will be somewhat our infrared with respect to this particular question. And one by one we can check the given options A, B and C and D. So we start with option A, which states that it goes from 2 to 1. So we can say our delta E will be equal to 13.6, and we have this as 1 square minus 1 upon 2 square, and this will be our 10.2 electron volt. And which is nothing but our ultraviolet. We have our option B, which gives us our 3 to 2. Our delta E will be equal to 13.6, and we have this as 2 square and 3 square, which will be approximately equal to 1.89 electron volt. And this will be somewhat near ultraviolet or somewhat visible. So we are going to call this as near ultraviolet. And we have our 4 to 2, delta E will be equal to 13.6, and we have this as 1 upon 2 square minus 1 upon 4 square, and this comes as 2.55 electron volt, and this will be completely in visible range. Visible. And we come to the last part, that is from 5 to 4, that is our delta E will be equal to 13.6, 4 square, and we have here 5 square, approximately equal to 0.31 electron volt, which will be nothing but our infrared. So the option number D is the correct one. Option D is correct. So in this case, we can just make a, you can say, approximation also of the result. If we see that for 2 to 1, it's the highest one, and from 5 to 4, it is the lowest one. So obviously, the highest energy, like we said, is going to behave for our ultraviolet, and the lower is going to behave for our infrared. Even if we are, if we are not able to identify what will be the in between, we can just go for the two extreme, and that will be giving us the result. In this case, that is part D. Next question. It was asked in the year 2001 and states that a radioactive sample consists of two distinct species having equal number of atoms initially. The mean life of one species is tau and that of other is 5 tau. The decay products in both cases are stable. A plot is made of total number of radioactive nuclei as a function of time. Which of the following figure best represents the form of this plot? So in this case, we are given that two species are there. Let us assume that we are given two species, and let us call them species A and species B. And initially it is said they are same, equal rather. So we can say Na naught will be equal to, for second, Nb naught. And their mean life is given. So we can say mean life for first one, that is tau A, it is given as T, and for our tau B, it is given as 5 times T. 5 times tau, sorry. So from here we can say that our tau, this species A, will be shorter lived where this B will be longer lived. And it also say, or we can say that, I think it is mentioned, it is mentioned that the decay products in both the cases are stable. Okay. So we can say decay products are stable. So which basically means that they do not add in the radioactive count. They do not add into radioactive count. It means the product are stable, so they are not basically radioactive. This is the simplest version. And we have to plot for the total radioactive of both A and B. So you can say total radioactive nuclei and let us suppose we call this as N total with respect to time t will be equal to width for sample A plus for species B. And according to radioactive law, let me write straightforward, decay law, it states that for a time t it will be equal to our n naught e raised to power minus t upon tau. So we have two samples, species rather, so we can write our NAT will be equal to, and they are having same, so let us assume this is equal to n naught, and we have this as n naught e raised to power minus, and here the, one second, oh my mistake, one second, this is our T of A and this is our T of B. So we get this as T upon tau, and tau, this will be our divided by T, giving us n naught e raised to power, one second, there is some, tau of A and tau of B. Let me rephrase it, and this comes as our tau of A. So this will be E minus T upon tau. And similarly, we can write that for B of T is equal to n naught e raised to power minus T upon tau B. And this is equal to our n naught e raised to power minus T upon 5 tau. And this can be further written as n naught e raised to power minus T, and this gives us our n naught e raised to power minus T upon 5. Now for the total, we just add them. So we get our n total for time t will be equal to n naught e raised to power minus t plus e raised to power minus t upon 5. So this is, and we can also find out here initial. So we can say at t is equal to 0, our total at 0 will be equal to, this comes as n naught plus n naught, that will be equal to twice n naught. So this will be initial value, and from here we can say initially the first part is going to dominate because it is going to decay rapidly, and the species B is going to decay slowly. Basically we can say that there will be a faster drop and then it will be asymptotically approaching 0, something like this. It will be more or less exponential. So therefore option number D is the correct one. D is correct. Small correction, I think, yeah, because like I said, at t is equal to 0, it is going to start from a value that is about 2 n naught. So it is going to start from here, drop very sharp, and then asymptotically reaching a 0 value. So option D is correct. Next question. It says that a radioactive nucleus X decays to a nucleus Y with a decay constant lambda x 0.1 per second, while further decays to a stable nucleus Z with a decay constant lambda y given as 1 upon 30 per second. Initially there are only X nuclei and their number is n naught 10 to the power 20. Set up the rate equation for the population of X, Y and Z. The population of Y nucleus as a function of time is given by this particular equation. And secondly, find the time at which n of Y is maximum and determine the population of X and Z at that instant. So we are given that we have a initial is our X, intermediate is Y and final is our Z. So this is basically a decay chain. So we can write that decay chain, it is given to us as it start with X and intermediate it is Y, and from Y it is going to give us a Z, and this Z is a stable, so it is not going to further decay or will not be contributing to the decay part. And we are given that for the first part lambda of X is our 0.1 per second and lambda Y it is our 1/30, and which will be approximately equal to 0.033 per second. And initially it is said that only X is present. So you can say initial condition we have only X, so we can write that our nx0 is equal to 10 to the power 20, our ny0 is equal to 0 and our nz0 is also equal to 0, and equation is given to us. So we can write that the equation is our n of y upon t is equal to our n naught, and this is our lambda of x divided by lambda of y minus lambda of x, and e raised to power minus lambda x t minus e raised to power minus lambda y t. We can just directly formulate our rate equation by the derivative. So we can write rate equations. First is our derivative of n of x with respect to time t, and this will be giving us minus lambda x n of x, and then we come to our derivative with respect to y and time t. This will be giving us lambda x n of x minus lambda y n of y, and finally we come to our z part. D of nz upon dt will be equal to lambda y and n of y. So rate equation were quite straightforward, and we can also write the equations. So we can write our n of x with respect to time t is equal to giving us a solution of n naught e raised to power minus lambda x t, and similarly we have n of y t giving us the equation given to us, that is our n naught lambda x lambda y lambda x, and we have this as e raised to power minus lambda x t minus e raised to power lambda y t, and we are left with now z. So we can write this as n of z t will be equal to our n naught minus nx t minus ny t. Okay, so these are the equations for our n rate of x, y and z with respect to time t. And for the second part, we have to find out the time when which ny is maximum. So we simply derive it and substitute the equal to 0. So you can say our time when n of y t is maximum, or we can say that our derivative of n of y with respect to time t is equal to 0. Its equation is already known to us, or we can just directly say that our lambda x e raised to power minus lambda x t will be equal to lambda y e raised to power lambda y t. And if we take natural log of both sides, we get this as natural log of lambda x minus lambda x t will be equal to natural log of lambda y minus lambda y t. So we have t as well t. Here t we can substitute as a t max will be equal to natural log of lambda y upon lambda x upon lambda y and divided by lambda x minus lambda y. And we already know these values. These are 0.1 and 0.003. So we get our T max will be equal to natural log of 0.1 divided by 0.033, and this comes as 0.1 minus 0.033, approximately equal to 16.48 seconds. And we have to find out the population at this particular time. So we can say population at T is equal to T max, which is equal to 16.48 seconds. So let's find out the for x. So we can say our nx at T max, this will be giving us nx is equal to n naught e raised to power minus lambda t, and initially n naught is our only n naught is present, so this is going to be 10 raised to power 20 e raised to power minus 0.1 into 16.48, and we can write that our nx at t is equal to T max will be approximately equal to 1.92 into 10 to the power 19. And for our y, we can write that our ny at T max, this will be giving us equation is known to us, and y is equal to 10 to the power 20 multiplied by 0.1, 0.033 minus 1 e raised to power minus 0.1 into 16.48 minus e raised to power minus, this is our 0.033 multiplied by 16.48. So we get our n of y will be approximately equal to, at t is equal to T max, will be approximately equal to 5.79 into 10 to the power 19. Similarly, we are going to find out our nz. So we have our nz at T max, which gives us nz is equal to our n naught minus nx and minus ny. All values are known to us. This is 10 raised to the power 20 minus 1.92 into 10 raised to the power 19 minus 5.79 into 10 raised to the power 19. And we get our nz at t is equal to T max is approximately equal to 2.29 into 10 to the power 19. Okay, next question. It states that it was asked in the year 2001 and states that in a nuclear reactor, 235 uranium undergoes fission, liberating 200 mega electron volt of energy. The reactor has a 10% efficiency and produces 1000 megawatt power. If the reactor is functional for 10 years, find the total mass of uranium required. So we are given energy released per fission is 200 mega electron volt and 10% efficiency, producing power is 1000 megawatt and time is 10 years. So we can find out the output power of our So let us find out our total energy output. Total energy output, that will be equal to, let us suppose, E out, will be equal to power multiplied by time t. Time t is again a 10 year and power output. So we simply substitute it. We get this as 1 into 10 to the power 9 watt, and multiply by time is our 10 year, multiply by, we have this as 365, this comes as days, and we come this as 24 multiplied by 3600. So the total energy output will be approximately equal to 3.1536 into 10 to the power 17 joules. And we are dealing with 10% efficiency. So we can say that energy produced by fission before efficiency loss. You can say total energy produced by fission before efficiency loss. Before efficiency loss. So which basically means we are going to find out the input energy. Okay, which means that suppose this is a black box in which the fission is taking place, and this black box is operating at a 10% efficiency, and we already know the output given by it is our E out. So based on this we can find out our E in. So we can say our E input will be equal to our E output, and it is 10%, so this is 0.1. This will be coming as 3.1536 into 10 to the power 17 divided by 0.1. So we get our E input will be equal to 3.1536 into 10 to the power 18 joules. And total mass of uranium is required, and we are going to convert our this energy per fission is given to us. Energy per fission, which we call as energy fission in a single fission, will be equal to, we have this as 200 and megawatt, so this comes as 200 multiplied by 1.6 into 10 to the power minus 13 joules, and this will be coming as 3.2 into 10 to the power minus 11 joules. So in a single fission we are able to get 3.2 into 10 to the power minus 11 joules. So number of fissions required, number of fission required, let us suppose these are n, this will be equal to energy at the input and energy of the fission, which is single. This gives us 3.1536 into 10 to the power 18, and this is 3.2 into 10 to the power minus 11. So we get value of n is equal to 9.8 into 10 to the power 28. Now we can easily find out the mass, and for that we require number of moles. So we can say total mass of uranium let us suppose that is M, will be equal to number of moles and multiply by molar mass. So we can say our M, that is the mass, number of moles will be equal to the given number that we found as 9.8 into 10 to the power 29 and divided by Na, that is the number of atoms per mole. So this comes as 6.022 into 10 to the power 23 multiplied by molar mass is our 0.235 kg per mole. Yeah. So this gives us that mass M is approximately equal to 38.4 tons. Next question. It was asked in the year 2001 and it states that a nuclear at rest undergoes a decay emitting an alpha particle of de Broglie wavelength lambda 5.6 into 10 to the power 15 meter. If the mass of the daughter nucleus is 2 to 3.610 AMU and that of alpha particle is 4.002 AMU, determine the total kinetic energy in the final state. Hence obtain the mass of the parent nucleus in AMU. So here we are going to use the concept of the momentum. So we can say that our momentum P is equal to hc upon lambda, and we can find out value of P. P is our H, we already know, is our 6. One second. Okay, so we are basically going to find out the value of momentum in terms of the unit. We are going to find out in terms of mega electron volt per C. Okay, so this is basically unit in which we are going to calculate it. So we need not to substitute value of C. Now let me do it in more traditional way, it will be helpful. So this becomes hc upon lambda, and we know that value of H is our 6.6 into 10 to the power minus 34 joule second, and we know our 1 electron volt is our 1.6 into 10 to the power minus 19, and value of C is our 3 into 10 to the power 8 meter per second. So first of all, we are going to find out our momentum P in SI units, which will be equal to 6.6 into 10 to the power minus 34, and lambda is given to us 5.76, into 10 to the power minus 15. This comes as 1.15 into 10 to the power minus 19 kg meter per second. Now we are going to convert this P into mega electron volt divided by C units. So this gives us that our P in terms of mega electron volt and C will be equal to, we are going to write this as P in terms of kg meter per second multiplied by C in terms of meter per second, and we are going to have our electron volt, that is our 1.6 into 10 to the power minus 13. This comes as joule mega electron volt, and this looks good now. So first of all, we are going to find out our numerator, that is P multiplied by C. P multiplied by C is equal to 1.15 into 10 to the power minus 19 multiplied by 3 into 10 to the power 8. This gives us 3.45 into 10 to the power minus 11 joules. And we are going to convert this into our mega electron volt. So we come this as our 3.45 into 10 to the power minus 11 and 1.6 into 10 to the power minus 13, which will be giving us to 1.6 mega electron volt C. And kinetic energy, so you can say that our kinetic energy of alpha particle, kinetic energy of alpha particle, that is our K alpha, will be equal to P square upon 2m. And we are required to find out mass of alpha. So we can say our mass of alpha, let me write this as of alpha, mass of alpha, and we are going to in units will be our mega electron volt per C square. So this gives us 4.002 multiplied by 931.4, which will be equal to 3727.1 mega electron volt per curie square. So we can say that our K alpha will be equal to, momentum we found out is 215.6 whole square and 2 multiplied by 3727.1, which will be approximately equal to 6.24 mega electron volt. And finally, we are supposed to find out total kinetic energy as well as the mass as parent nucleus. Okay, now we can easily use the conservation of momentum and energy with respect to the daughter as well as the total kinetic energy. So we can say conservation of momentum and energy, conservation of momentum and energy, and initially they are at rest. Initially nucleus is at rest. Therefore, we can write that momentum of alpha will be equal to momentum for the daughter, or we can say that mass of alpha, velocity of alpha is equal to mass of daughter and velocity of daughter, and their respective kinetic energy. We can say kinetic energy of alpha is equal to p square upon twice mass of alpha, and kinetic energy for the daughter will be equal to p square upon twice mass of the daughter. So from here we can just find out the ratio. We can say our k alpha upon k daughter will be equal to mass of daughter divided by mass of alpha. And k of alpha, we know that the energy associated with alpha particle. So we can say our kinetic energy of the daughter will be equal to kinetic energy of alpha multiplied by mass of alpha and mass of the daughter. And this is 6.24 multiplied by 4.002 divided by 2 to 3.610. This will be approximately 0.0, sorry, this will be 0.112 mega electron volt. So the total energy released will be the summation of the kinetic energy of the daughter as well as the kinetic energy of the alpha. So we have total kinetic energy released, if that is k total, will be equal to k alpha plus k of daughter, and we get this as total will be equal to 6.24 plus 0.112 approximately equal to 6.352 mega electron volt. Now we can use the mass energy conservation principle and find out the mass of the parent nucleus. Mass energy conservation we can write that mass parent c square is equal to mass of the daughter c square plus mass of the alpha c square plus kinetic energy total. And in terms of AMU, we can write this as mass of the parent is equal to mass of daughter plus mass of alpha plus kT divided by 931.4, and this is in terms of AMU. And okay, here we have to remember that the energy release is positive, so the mass of the parent will be, oh yes, this has to be minus, my mistake, minus, okay, because this lost mass will be converted into kinetic energy. So we simply substitute the values, and we get this as mass of daughter, that is about 23.610 plus alpha is our 0.02 minus total energy we found out is 6.352 divided by 931.4. So from here we get our mass of the parent will be equal to 227.605 AMU. I think this was the, finally we were asked that the mass of the parent. Yeah. So here we have to just remember that this kinetic energy is the representation of the mass lost. So that's why we are going to, this is representation of the mass lost converted into kinetic energy, into kinetic energy. So that's why it should be minus, not positive. So this completes all the 10 questions, 5 from 2000 and 5 from 2001. So this completes all the 10 questions. Thank you.